So now we got to talk about randomness, which is kind of crazy. You need random numbers in cryptography, but it's actually pretty hard to define what random is and to measure whether something is really random enough. And in fact, there have been some serious problems caused by random numbers not being random enough. So, I mean, here's an old Dilbert cartoon about it. A random number generator just gives him 9 6 times. And he says, are you sure that's random? And that's a very good question. I mean, that could happen if it was random. You don't know. So how do you tell? So is this more random than that? Most humans will say, this looks random, that doesn't look random. But in principle, they're equally likely, this pattern of exactly those bits. But the point is, when you look at this, you don't really memorize this sequence of bits. You just say, oh, it looks like about an equal mixture of ones and zeros. And if you consider everything that's approximately equal mixture of ones and zeros, there are a lot more of them than there are of this. So you have to consider how much information did you really extract from that. So, all right. So you can measure it as a probability distribution. So if you have a fair coin, you have 50% chance of heads and 50% chance of tails. Fair die, you have 1/6 chance of each of the 6 titles, and so on. So that's a uniform distribution where you have an equal chance of every outcome. And so you can mathematically measure this with entropy. Entropy is the statistical, so if you have the probability of n possible outcomes here, then the entropy is P1 times log P1 minus P1 minus P2 times log P2, and so on. You just define it this way. And all these logs are negative because the probabilities are all less than 1. So this is a positive number. And if you make it the log to base 2, this is called Shannon entropy or Shannon information. It is a measure of the amount of information in this thing in bits. So if you have 1 random bits with half and half, then the entropy is minus a half log a half, and log of a half is minus 1. So this is 1 bit. So something that has 50% chance of being 1 and 50% chance of being 0 has 1 bit of information, which is pretty logical. That's what you would figure. And so if you have a random byte, you have 256 possible bytes. Each one of them has 1 256 chance of hitting. So the entropy is 1 over 256 log of 1 over 256. This log is minus 8 because that's 2 to the 8. So it's minus 8 256, but there's 256 terms, so you get 8 bits. This is why Shannon entropy is logical. A random byte has got 8 bits of information. It takes 8 bits to specify it. And if, for example, if you had an ASCII character that only uses 7 of the bits, because it only goes up to 127, then you'll find it works. You're going to end up with just 7 bits when you do this math, because there's really only 128 possibilities. So that's the point. That's why Shannon noticed this and said this entropy concept from thermodynamics, in fact, works pretty well to define the amount of information stored in something. All right. Now, let me just check for comments on the Twitch. Is this class? Yeah, this class is cryptography tonight. Yeah. All right. So if you have a non-random bit, like 99% of them are 0 and only 1% of them are 1, then the entropy is this. Now the log of 1 is 0. This log is almost 0. And so you end up with 0.08. So you have less than 1/10 of 1 bit of information here. And of course, if it were all 0, you'd have 0 information. So you do 99.99% 0, you're going to get the entropy of 0.001. You have only 1/1000th of 1 bit of data there. As you understand, this kind of something like that, it's going to be almost no information there. It's almost all zeros. And if there's no randomness, entropy is 0. If there's really no variation. All right. So you can write Python to do this for you if you like. It's fine. But that's how I did it. Doesn't really matter. All right. So that gives you the general idea of Shannon entropy. Let's try some Kahoots about it. I've got them here. 2A. All right. Yep. All right. I think there are some more people on Kahoot, on Twitch. Only 8 though, so there might not be very many. We'll see. I I think they can see it though. Let me check. Oh, well, they should be able to see it. Yeah, they can see it. Okay, good. There they come. Good. I think so, yeah. Claude Shannon. Yeah, they did a lot of things. The main thing I know about him is the statistics and stuff, but he did a lot of things. Right, yeah. Yeah, that's what works. And in thermodynamics, random motion of atoms will always go to maximum entropy. That's because entropy is maximum disorder. If you have a hot area and a cold area, they will blend together to make a lukewarm area. Everything will even out. That's the state of maximum entropy. It also defines time. This is why time goes forward. Time is the direction of increasing entropy. And that might be all there is to it, too. Well, looks like there are only two people here. We'll carry on anyway. Such is life. All right. All right, so what is the log to the base 2 of 1/4? Good, you folks know your math. This is 2 to the minus 2, so the log to the base 2 is minus 2. Good? All right. All right, what's the entropy of one random bit? Or equivalently, the information content is the same thing. That's one bit of data. If it could be one, yep, and see, if somebody put 0, it's not, if the entropy was 0, that would mean no information can be encoded. But if you have a bit that can be either 0 or 1, then there's one bit of data there. All right. All right, what's the entropy of a random byte? That's 8 bits, right? You have 8 bits of data there. All right, 8 bits of information there. All right, how about a single random base 64 character? It's 6 bits. 64 is 2 to the 6. So if you have 6 random bits, that's 6 bits of data. And that's the point of base 64. So that's 6 bits there. That's why if you have 4 base 64 characters, it's the same as 3 bytes. You have 24 bits then either way.
Can you repeat this?
Yeah, so if you encode things at base, let me just do it in Python actually. Let's go terminal. All right, and let's go here, Python 3. All right, if I import base 64, okay. No, it's good, lowercase, that's the different case, base. Okay, then I have, okay, if I have a string is ABC, and I print base encode. I think it's this. I might have to Google the right answer. All right, let me, I've forgotten how it is. B64, all right, Python, encode, encode with base 64. I've done this a million times, but I forget. There we are, the import base 64, base 64.b64 encode. Okay, that's what it is. All right. This should be bytes. All right. There we are, of A. There, this is what I wanted to show you. So if you have 3 ASCII characters, which is 3 bytes, that turns into 4 bytes of base 64. Because each one of these only has 6 bits. So 2 of them is 12, 4 of them is 24 bits, and this is also 24 bits. So the A contributes this whole character in the first 2 bits here, and the B, the first 4 bits of that are included in the U, and the next 4 are included in the J, and so on. This is a string of 24 bits, and this is also a string of 24 bits, encoded in a different way. That's a good thing to know. All right. So, I think that was it. Oh, we're doing these Kahoots still. So, all right. I think that's it. All right. So there's only 2 players, so there's not much difficulty figuring out who wins. Tark. All right. So, put it on. So, let's get back to the slides. All right, so we'll talk about random number generators. How do you make these things on a computer? Now, having a real physical process like rolling dice would be best, but you typically don't have that, so you need a source of entropy somewhere. And then you need some algorithm to create random bits from the entropy. You have to have some source of randomness. So the random comes from the environment typically, so something like temperature, acoustic noise, random electrical fluctuation, mouse movements, key presses. You need some kind of random event coming in from the outside to provide randomness. Some people like quantum random noise generators. You have something like radioactive decay or photons, which are intrinsically very random and not very sensitive to things like temperature and such. Then you can have a pseudo-random noise generator. If you have a few really random bits, you can then run it through some pseudo-random system that creates more bits out of it. And therefore continues working even if you stop having the physical source come in, for a while anyway. So it receives random bits, it updates an entropy pool, and it mixes the pool's bits together when updating. So it does something, that's the plan, and so it uses a deterministic random bit generator that takes some bits from the entropy pool and creates a much longer sequence. This is deterministic though. If you knew the bits in the pool, you could predict the output of the deterministic generator. And this is going to turn out to be very important to us. This is essentially what encryption is, like AES. You take some input bits and you create some output bits that appear random, but in fact it's deterministic and you can reverse it back to decrypt it. So init initializes the entropy pool, refresh updates it using some data from the RNG, and then next returns the next block of bits. These are the typical functions of your pseudo-random number generator. Yeah.
Just a question, because
Yeah.
there was a question on the quizzes
Yeah.
that was saying something along the line, which of these stages, which of these operations moves the elements from the random number generators to the pseudo random
Yeah.
number generators? And I think if I remember correctly, the answer was init or refresh.
Yeah, I've forgotten. This initializes the pool.
Initializes, but it doesn't move.
No, that's what I thought. Rest seems to me like what does it. This is what actually uses the data from the random number generator. What's that?
211. This way or that way?
Another room?
211.
Well, this is 218, I think it that way. Because I
Okay,
think
good.
it's going in degrees.
Okay. I'm glad you know. Yeah, I'm having trouble understanding your question. Yeah, this is the one that actually uses up some of the entropy from the pool. So I'm not sure what that question was. Yeah. Yeah.
Okay.
But that's
because
the one,
I replied that none of them
Yeah.
was wrong.
Yeah, well, maybe the question's not very good. I don't remember. Yeah.
No,
Anyway, that's
just
good.
understand.
Yeah.
Okay.
Okay, and so there's an issue here, which I think we're going to get to. The early ones would actually stop creating numbers when they ran out of the pool. And that would seem like the right thing to do, but that turns out to be worse than the alternative. So we'll talk about this. Here's security concerns. One is called forward secrecy. Can you measure the bits and recover the old bits from it, and prediction resistance? If you take a sample of the bits, can you predict the ones before or the ones after? And you don't want either of these to be possible, of course. And so the NSA, for example, is capturing tons of encrypted traffic for almost a decade, maybe even more. They've been archiving all the traffic on the internet, hoping they will be able to find the keys. And they do periodically find the keys. They impound criminals' servers and find keys on them. So as time goes on, they're able to crack more and more of this archived data. So this is actually an attack that worries people a lot these days, because we have strong reason to believe that in about 20 or 30 years, quantum computers will crack our current systems of encryption. And therefore, what we're doing is not safe. Somebody could save that data. Now the question is, do you care if they decrypt it in 30 years? And for some things, like maybe financial transactions, you don't really care. But for other things like medical data, you might very well care. And so that's why people want us to move to quantum-proof systems now, as soon as possible, so we don't create more stuff that might be cracked later. So anyway, that's the actual place. Let me check for comments in the Twitch. There we go. All right. So I have a question regarding CNIT 50. When you tried to add, you're unable to. Well, okay, I'll talk to you at 7:30 and we'll see. Right, you don't need an add code, Yomi. Just make an online request. But we'll try this at 7:30. I can help. For a person who is unable to get in CNIT 50, I probably cannot help. They're incredibly ruthless here. If you don't make it in on the first day, there are no late ads. But we'll talk about it at 7:30. An important question, and I have a clear answer, but not a pleasant answer. Anyway, so here's what that means. Your refresh and next operation should be irreversible, so they can't predict the past, and it must refresh regularly with fresh random numbers, so the forward doesn't become predictable. So Fortuna is one Bruce Schneier and Niels Ferguson defined. This is what Windows uses for 32 entropy pools. Mac OS and iOS use something called Yarrow. These are just ways of taking the random bits and combining them with something like a hash function to create more. So if it doesn't produce enough random bits, Fortuna might not notice and just keep producing lower quality random bits or stop delivering bits. Now, if you were to reuse the same seed files, then you would get an identical sequence of output bits. So most of these things are called non-cryptographic. They create statistical randomness, but they don't worry about predictability. This is what a lot of the random number generators in cryptographic and programming languages are like. Therefore, there are a lot of people that write software without understanding that the normal random number generator is not good enough for cryptography. You have to get a better one. And many programmers have made the mistake of shipping products using the low-quality random number generator because they don't understand. The normal random number generator is just there to make things like games. And of course, because I think the early people designing the languages and libraries didn't really understand what they were doing too well.
You mean the one that is provided?
Yeah.
In this
Yeah. There's usually a random one that's the normal one that's not very good, and a special one you should import for statistical strength, or for cryptographic strength. So urandom gets data from the crypto pseudo-random number generator, and it's non-blocking. You will always get data even if the entropy is low. This is the one that will block and refuse to return data if the entropy is low, dev-random, as opposed to urandom. And people argued about this. At first they said you should block so people never get bad random data, but then what happens is it runs out of entropy quickly, and that creates a denial of service. So in practice, it turns out using urandom is better. So there's always random numbers when you go for it. I remember I hit an amazing situation of this when I installed a Java-based hacking product on one of my servers, and I booted it up, and it wouldn't come up. And I spent a long time trying to fix it. And then finally one day, I spent hours researching, fixing it, and it came up. And it took 45 minutes to boot up because the Java needed some random seed, and it took that long to get enough random bits in the pool. And I had to install a product called Haveged, Haveged, is a program to create more randomness, and it boots right up after that. It creates enough random bits so Java can find them. So that was an issue where the blocking was baffling me.
Sam, when
Yeah.
you say creating more randomness,
Yeah.
do you mean enlarging the range of...
It probably means they were not really all that random. It was, because I think what the problem is there wasn't enough in the pool to create truly random bits. But Haveged would do something like this non-blocking system where it creates bits anyway, even if it's not able to really have enough randomness.
Okay, because the way I'm understanding is, okay,
Yeah.
the random number generator
Yeah.
gives you, let's say, a handful of bits or
That's right.
entities.
Yeah.
So is the pseudo number generator that adds additional bits to that pool?
Well, it does something like take the clock and XOR it with that or something
And
to make
XOR,
more
okay.
bits. But it can only create so many bits before it's used up the random bits. And then what should it do? And the blocking one will stop until more random bits come in. And if you have a cloud server, there is no keyboard, there is no mouse. So I don't know what it uses for random bits.
For
Apparently,
sure.
there's not much, so it takes a long time to build them up. Um, and uh, and that's why switching to a non-blocking one makes the server boot up quicker, but it's probably not as random. And those are really your only choices, unless you add a hardware random source, which you can buy. You can buy a board just to make random bits that contains like a radioactive source or something.
Well, if a system boots, it means that all the connections get in sync, so
Yeah.
it's not random.
Well,
by
you
definition.
can make there are random number generators. In fact, modern processors, CPUs from Intel, have hardware random number generators in them, which is like what you do is you take a resistor, you run a current through it, and then you magnify the noise, and the random atom of the motion of the atoms creates some variation, and so that's built in, and that's what boards do. You can make, but and we'll talk. That's what I mentioned. Havaged is what happened to me. Tomcat took 45 minutes to boot up, but Havaged refreshed the random pool faster, so it did boot up quickly. And so I used to do this before 2022. I could watch this. You could see the entropy pool by just doing this, and you could then consume entropy here by just reading random things and printing them out. So this will look at the random entropy available. There's a measure inside the operating system, and this will use up the entropy. So you can, without Havaged, I could very quickly drain the pool down from like 2,000 bits of available stuff down to almost nothing. But when I installed Havaged, it would just stay at 2,000 all the time, because Havaged keeps filling up the pool with probably less perfect randomness, but at least the pool didn't end empty.
That about 2,000 can
Yeah.
be considered the size of the random pool, right?
Yeah, apparently so. Yeah,
Apparently.
yeah. And this is an old version of Kali, so I suppose there's an adjustment in the operating system of how big the pool is. Yeah. Yep. And so anyway, 256. Now they overhauled this thing, and now it always has 256 bits of available entropy, and you can't drain it. This is the new system. So this was an old version of Linux where you could watch this happen. In Windows, it's got this thing, and this is loosely based on Fortuna. And like I say, it's in 2012. Intel has a hardware random number generator in it. It's only partially documented, though, and around this time, some serious cryptography scandals came out. How a lot of big companies were lying about their cryptography and being forced to lie by the government to tell people to use unsafe cryptography, so people were very, very afraid of this. And so this was the big one, dual elliptic curve pseudo-random number generator. Microsoft researchers figured out, see, the NSA told people to use this particular elliptic curve with these certain parameters, and they did not say why. And what these guys figured out is they could have generated those parameters from secret numbers, and if they did, they'd be able to predict the output. And they wouldn't explain why, and so they said they might have put a backdoor in the random number generator. And this is what Bruce Schneier said. This is the best place to put in a backdoor. He said, if you're going to put a backdoor in cryptography, putting it in the random numbers is the best, because it's very hard for anybody to figure it out. And if you don't leak out the secret, it really is what you want. Nobody else can use it. Just the people that have the secret numbers can get in, and that's what they look for. In the spy community, they call this no-bus, nobody but us. They want to have a backdoor that nobody can use but us. And this would work if you could keep the secret numbers secret. Unfortunately, the NSA has leaked out so many secrets with Snowden and many other times. They don't seem to be very good at keeping secrets, and that kind of is their whole job. So people have little faith in them to trust them with these no-bus systems. So that's the game. They say they're not proving it, but what they are saying is it's dependent on one particular instance, and it could be that there's a secret number. So one thing that's very strange is the recommended algorithm is 1,000 times slower than other options, and the NSA paid like RSA $1 million for them to make it the default. So it's very suspicious. It's not like it's the best algorithm. It's very much like they pressured them into using it for some hidden nefarious reason. So people didn't trust it. And there were some secret documents that came out from Snowden talking about how, in fact, the NSA did, in fact, practice tricking people into using insecure stuff. They actively engaged U.S. and foreign IT industries to covertly influence and overtly leverage their commercial products' designs to make the systems exploitable with foreknowledge of the modification. And here's the program they had to insert vulnerabilities into commercial encryption systems and influence policies and standards for commercial keys. So the NSA, the Snowden leaked out the fact the NSA was absolutely doing this. They were poisoning the well. They were tricking and forcing people into making insecure products just so they could get in, which is their job. I mean, their job is to spy on what people are doing to catch the bad guys. So they're doing their job, but their job is kind of contrary to the general good, especially if they're going to do stuff like let the Russians steal it and release WannaCry and shut down the hospitals, which is what happened. I mean, if they only used it to catch terrorists, then maybe nobody would be mad. But in fact, a lot of bad things happened, making people rebel. So they abandoned this because they're worried about it. And so there's other ways things can go wrong. So you might have a poor entropy source, and Netscape seeded it from the process ID and the system time, and that was predictable. So that's not good.
But was predictable because of the choice of the unit of measure, the microseconds?
No, it's predictable because there's nothing really random there. It's the time since you booted up the machine and the process ID, which is pretty predictable too.
I bet.
So if you made like a random seed for your cryptocurrency, all I'd have to do is like look at your chat log and figure out when you turned on your machine and then guess how many programs you've launched. It wouldn't be too many options to predict this thing. That's the thing. So the total entropy was only 47 bits too. And here's another one. This one hit a lot of people. Remember, all over the world this hit. In 2012, a guy took all the HTTPS certificates on the web and checked to see if any of them were sharing common factors. If you have two numbers that are the product of two prime numbers, but they're same prime number, then they can divide each other. It's a very simple test. So and there's only like 100,000 certificates in the world, so you can just write a Python script to try dividing them all by pairs, and he found that 1 in 1,000 of them were in fact matching. So the random numbers, they're supposed to be like 200-digit long random numbers used for RSA keys. They should never be identical, ever, in the whole universe, and like 0.1% of all the ones on the internet were in fact identical prime numbers. So that was disturbing. And so I tried to figure out why. There are all these theories, and the ultimate conclusion that people came to is that it came from devices like firewalls, where they're all exactly identical hardware. You turn them on, they boot up, it takes so many microseconds to reach the point where it makes the random key, and there's a pretty good chance that two of them will in fact create exactly the same so-called random number, because there is no real randomness. They're just using something like the system clock and the process ID, and they're identical hardware, so they have a pretty good chance of having exactly the same state at that critical moment when they somehow calculate a random number.
And this is particularly true at the boot up, because at the when you're rebooting the machine,
it's just going through the same steps.
Yeah,
exactly. Yeah, and it wasn't like they were all the same, but it's fairly common that they happen to create this so-called random number that is exactly the same random number another copy of the same device will make. So here's another one of these, which is not very secure, that people had something else that can go wrong. This was used for Wikipedia. It was a Mercian twister, which was not random enough, really. And another thing you can do, CryptoCat was now, if you remember the Arab Spring around 2011, all these people were rebelling against the government in the Mideast, and they were organizing their protests on Twitter, which was completely unencrypted at that time. And so it was very easy for the government to track down people and predict a protest. So this activist made an encrypted chat called CryptoCat when there was no Signal, there was no instant Facebook Messenger, there wasn't another encrypted chat at that time. So he wrote his own encrypted messenger, and the information security community complained greatly, saying his encryption was pretty lousy. He said, well, it's better than Twitter, which is no encryption at all, which is true, but he wasn't very good at it. So he had an off by one error, and again, he had 45 bits of entropy instead of 53, so it wasn't hugely wrong, but people got all mad that this guy's sloppy, he doesn't know cryptography very well, which was all true. He didn't really know much, and so he improved the product. But anyway, there have been quite a few products that turned out to be insecure in various ways due to not enough randomness. Anyway, let's take a look at 2B here in the Cahoots. That's right.
So I should actually get, if in two different instances I choose the same sig, I should retrieve
Yes.
exactly the same sequences
Yes.
and numbers produced.
Absolutely. And if you remember the machine learning class you did last semester, I did this. You set the seed, and then all the students will get the same answer. That's the idea. Yeah. Yeah. Yep, that's right. Yeah. And that's apparently what was wrong with those firewalls. They would end up with essentially the same seed sometimes.
So this means that choosing a seed as some sort of a constant on these random bits.
Well, it should be really random. So you should get some randomness somewhere, like from the motion of the mouse or the electrical noise or something. You need some actual random data.
Right, but if you mix a randomness with randomness, very likely you get randomness.
Yeah.
But if you mix randomness with linearity, predictability, you end up being more predictable.
That's right. Well, there's a limit. That's right. So if you have only 8 bits of randomness, then there's only 256 possible seeds. And so measuring the output, after you measure, say, maybe 256 numbers, you can probably guess what the seed is. So, I mean, more randomness would give you more time before it starts repeating. But it will eventually repeat or show a pattern if you only have so much real randomness in there. Yeah.
Because when I was using modeling in the causal inference, I was using a technique called the propensity score analysis, in
Yeah.
which you predict an outcome based on measures.
Yeah.
And if you have to repeat that kind of analysis, you have to remember the seed that you chose and you started.
Yep, to get perfect reproducibility. Yeah. Anyway, all right, let's try this stuff. So we got some people. So I guess you can see the number. Let's take a look here. Yes, good. All right. So I'm going to go here and run it if I can find it. There we go. All right. All right, so which one harvests entropy from keyboard and mouse inputs? Yeah, that's random number generator. That's the typical kind. And there used to be true of OpenSSH. I think of OpenSSH, OpenSSL, when you generated an RSA key, it would make you move the mouse and type until it was able to get enough randomness to make the random key. All right. All right, so which one updates the entropy pool? It's PRNG. I would argue the RNG also, in a pure random number generator, has a pool. It pulls some random bits and puts them in the pool. All right. And which algorithm does the Mac use? Uses Yarrow, Microsoft uses Fortuna. Anyway, all right.